So just a couple more of these inverse Laplace transforms, and again we're trying to get to the more advanced type and show you the techniques of these. So we have this Fs is equal to s over s squared plus 4 s plus 2, and here's an error that students commonly make, is that they see that it should be a decomposition because they notice that there's two binomial factors in the denominator, and they will write this as a over s squared plus 4 plus b over s plus 2. But unfortunately, that is not the correct composition. And the reason that is because this s plus 4 is a quadratic. And remember that the numerator always has to contain an undetermined polynomial such that the degree is 1 less than the denominator. All right, so let's write this the correct way. And instead of just a in the numerator, we're going to write that as as plus b. So we have a linear polynomial in the numerator, we have a quadratic polynomial in the denominator. We still have to concern ourselves with the c over s plus 2, but that's not so bad. All right, so hopefully that makes sense as to the decomposition rules. At this point, we're going to go through, we're going to multiply by the common denominator, and we're going to rewrite this as as plus b times s plus 2 plus c times s squared plus 4. Right? And then at this point, we can go ahead and distribute. So we're going to wind up with s equals as squared plus 2as plus bs plus 2b plus cs squared plus 4c. And now what we can do is we can group the like s terms, or the like s powers, and kind of match them up to the left-hand side. Now it might behoove us to write this as 0s squared plus s plus 0, right? And that way we're set up nicely to be able to create our system. Okay, so and then on the right-hand side, we have an as squared and a cs squared. So we can write this as s squared a plus c. We have a 2as and a bs. So we can factor the s out of that and be left with 2a plus b. And then finally, we just have 2b and 4c. As our coefficient of s to the 0 power, or just non-s. And so now what we can do is we can match these up just like we've done a number of times. So we know that 0 is going to match up to a plus c in our system. So 0 equals a plus c. We know that s1 is going to match up to 2a plus b. And then finally, we know that the other 0 is going to match up to the constants, so 0 is going to be equal to 2b plus 4c. All right, and now we can go ahead and solve this system to hopefully be able to get some sort of relationship between a, b, and c. All right, so we know that, first of all, a equals negative c, and we can just go ahead, substitute that right into here, and we're going to get our system that 1 is equal to minus 2c plus b, and we have 0 equals 2b plus 4c. Right? And then we can go ahead, we can go back through and maybe solve this. So what happens when we solve this? So if we get that, we're going to subtract 2b from both sides. So negative 2b equals 4c, or b equals minus 2c. And then we can just plug that back in up here. We get 1 equals negative 2c minus 2c, and clearly negative 1/4 is going to be equal to c. Now let's hold on to that because that makes a really easy, because remember a is equal to negative c, which means that a is 1/4, and then mercifully we can find out what b is. Remember that b is related because b is equal to minus 2c. So b is equal to negative 2 times negative 1/4, or 1/2. All right, so hopefully that's okay with everybody so far, just some algebra. And now what we're going to do is we're just going to go back and we're going to remember that this was the decomposition that we were looking for. Okay, so let's just substitute A, B, and C back in, right? And so now we're going to get a decomposition of 1/4 S plus 1/2 over S squared plus 4 plus C, which was negative 1/4 over S plus 2. Right? And now what we can do is we can go ahead and now try to find the inverse Laplaces of these expressions. Now, we're going to have to be a little bit slick about the first one. And what we can do is we can rewrite this as 1/4 times S over S squared plus 4 plus 1/2 times 2 over 2 times 1 over S squared plus 4. And I'll explain that in a moment. Minus 1/4 times 1 over S plus 2. All right. So what I did was I just broke up the first fraction into two fractions. And I also multiplied by 2 over 2 because I noticed that right here, our k has to be equal to 2. Now, we might not be sure if we have to use sine or cosine, but it does fit one of the two forms. And because it doesn't have an s up top, it's probably going to be the one to where we have to use k over k squared plus s squared plus k squared. All right. The rest of them should be fairly straightforward at this point. All right. So now we're set up, and we can go ahead and find the inverse Laplaces. So now we can do 1/4 inverse Laplace of S over S squared plus 4 plus 1/4 inverse Laplace, so 2 times 2 in the denominator, of 2 over S squared plus 4, and then finally the sneaky one, or not really all that sneaky, but 1/4 Laplace inverse of 1 over S as S approaches S plus 2, because we have that first translation theorem. Okay, so we have to be really careful when we see these translation theorems, because we could have thought the translation theorem could be used on S squared plus 4, but it has to be a linear term. Okay, so make sure that for S squares that you think about sines and cosines. All right. Finally, we can go through. We know that k is going to be equal to 2, k is going to be equal to 2 here, and the inverse Laplace of 1 over s is just 1. Right? And so our answer is going to be 1/4 of the cosine of 2t plus 1/4 of the sine of 2t, right? So that's cosine, this one's the sine, and then finally minus 1/4 times 1, which is the inverse Laplace of 1 over s, and then times e to the minus 2t. Right? If we wanted to factor out the 1/4 and just clean that up just slightly, we could write this as cos 2t plus sine 2t minus e to the minus 2t. Right? So pretty cool on that one. All right, we still have to use partial fractions to be able to solve it, but this is what we end up with. Right. Now, one last example, and this is unlike any of the ones that we've seen before. Doesn't mean it's any more difficult or easier. So we have s squared plus 6s plus 34 in the denominator, 2s plus 5. How is it different? Well, unfortunately, this is a prime polynomial, so we can't factor it. Right? One of the techniques you might remember from Calculus 2 is sometimes completing the square helps out a lot, and this is one of those sometimes. We're going to rewrite this as 2s plus 5, and I'm going to rewrite s squared plus 6s, and I know to complete the square here, I need a 9. And we know that 34 minus 9 is going to give us 25. So I'm just going to rewrite that 34 as 9 plus 25. Right? Now, fortunately, whoever gave us this problem realized that when you split up 34 into 9 plus 25, that gives us two very nice perfect squares. And so now what we can do is we can rewrite this as 2s plus 5 divided by s plus 3 square plus 25. Now, we're not done yet, all right, but at least we're in better position. Right? It would be really nice if somehow the numerator had s plus 3 in it, because then we could use the first translation theorem. So what we're going to do is we're going to bully the numerator to look like it has an s plus 3. And here's how we're going to do that. We're going to rewrite the numerator as 2s plus 5 plus 1 minus 1. This is actually a trick that we used when we were able to find the series solutions of about an ordinary point that was non-zero. Remember, we added and subtracted a specific value. And I'll show you why we add and subtract that specific value in a moment. S plus 3 square plus 25. So far, all algebra. We're going to now rewrite this as 2s plus 6 over s plus 3 square plus 25 minus 1 over s plus 3 square plus 25. Okay? Or, and I think a lot of you are probably seeing what we could use in the first fraction, instead of 2s plus 6, couldn't we rewrite that as 2 quantity s plus 3? A lot of these types of inverse Laplace problems involve a lot of pattern recognition. And so if you recognize those patterns where you need an s plus 3 and an s plus 3, and then you can add the right number, then it works out really nicely. All right, so what do we have? Well, we have some really nice inverse Laplaces going on as s approaches s plus 3. Now we know that in both of these, k is going to be equal to 5. So the second one isn't completely set up, but it's mostly set up. So let's just multiply the top and the bottom by 5. All right, so we've seen that trick a number of times, and now I think we're almost set to do this. So now we can rewrite this as 2 inverse Laplace of s over s squared plus 25 as s approaches s plus 3 minus 1/5 inverse Laplace of 5 over s squared plus 5 as s approaches s plus 3. Right? And then finally, we can just go ahead. We recognize the first one as our cosine function. We recognize our second as our sine function. We can't forget that these have the first translation theorems on them. And so for our answer, we're going to write this as 2 cos of 5t times e to the minus 3t. Okay, so notice right here, a is negative 3, minus 1/5 sine of 5t, e to the minus 3t. All right. And we can leave it like that. In fact, we will leave it like that because I'm out of room and I don't feel like necessarily making a new line for this. All right, so bottom line, inverse Laplace transforms are sneaky. They require a little bit of foresight and a little bit of trickery for us to be able to manipulate them. However, it's all algebra. Okay, so hopefully these videos have given you a good idea as to some of the techniques that are necessary to manipulate these expressions to force them into to being good inverse Laplace transform candidates.